Hello dear students, I am Samir Velankar. I welcome all of you to this video which is based on the topic recurrence relation for dividing functions or as dividing functions. Now in the previous 3-4 videos we have been seeing the recurrence relation for decreasing functions, and those recurrence relations were of the form Tn is equal to A into Tn minus B plus Fn. For instance, we had a recurrence relation like Tn is equal to Tn minus 1 plus 1. So n, the data size, was getting reduced due to each recurrence call. Due to each recursive call, the data size used to get reduced by the amount of b. Now from this video onwards, we are going to see another type of recurrence relation in which the data size n doesn't get reduced by some amount, but data size n gets divided by some amount. Just check the recurrence relation where Tn is given as A into Tn by B plus Fn. So data size n is getting divided by some constant. As an example, I have written a recurrence relation in black over here. Tn is equal to Tn by 2 plus 1. Now notice each time the recursion occurs, the same function is called by reducing n, not by some constant amount by subtracting it, but by dividing n with some constant like 2. So Tn is equal to Tn by 2 plus 1 is the recurrence relation if n is greater than 1, but Tn is assumed to be 1. This is base case. Tn is 1 if n is 1. So we know that T1 is 1 because it is given that Tn is 1 if n is 1, isn't it? Now we would like to know the complexity that will arise due to this recurrence relation. We will be using the same method of substitution. Then we will be seeing the tree method to solve this recurrence relation. You all know that tree method is nothing but almost same as method of substitution, only representation is different. And third thing I will tell you about this dividing functions, very interesting. I'll be teaching a theorem called Master's theorem in the later videos, where we will see how we can find out the complexity of dividing functions within seconds using Master's theorem. But for this video, we are going to see method of substitution. So let's take this recurrence relation. I have written it again here. Tn is equal to Tn by 2 plus 1. Of course, if n is greater than 1, let's number this as equation 1. Now you see, if Tn is Tn by 2 plus 1, then what is Tn by 2? Just a question mark. What is this Tn by 2? It is easy to see that Tn by 2 is Tn by 4 plus 1, because given the equation Tn is equal to Tn by 2 plus 1, Tn by 2 plus 1. What will be Tn by 2? Well, what you will do is you will just put on this left hand side here, instead of n, you will put n by 2. Isn't it so? So if you put n as n by 2, you will be putting on the right hand side here, this n also will be replaced with n by 2. So it will be n by 2 upon 2, that will become n by 4. Isn't it? So Tn by 2 will become equal to Tn by 4 plus 1. This 1 will stay. So that is what I have written And we are now seeing that this Tn by 2, Tn by 2 is nothing but Tn by 4 plus 1, isn't it so? Now what do you do is in the method of substitution, you just put this value. This is the value of Tn by 2 in the place of Tn by 2 in equation 1. So on substituting this value of Tn by 2 in equation 1, we get equation 2 here, which will be Tn is equal to Tn by 4 plus 1. Now just check this Tn by 4 plus 1 is nothing but Tn by 2. And then that plus 1, which we had in equation 1, stays as it is. Okay, so again, what is Tn by 4? Now I hope you have understood now enough. Yes, that Tn by 4 in this equation, equation 2, this Tn by 4 is going to be nothing but Tn by 8 plus 1, isn't it so? Because in our equation, Tn is equal to Tn by 2 plus 1. This is our equation, isn't it? N by 2 plus 1. So what you will do to find out Tn by 4 is, on the left hand side here, instead of n, you will be putting n by 4. That will give you Tn by 4, isn't it? So obviously on the right hand side, this n also will be replaced with n by 4. So it will be n by 4 upon 2. That will be n by 8. And this plus 1, the plus 1 will stay. So Tn by 4, here we are, Tn by 4 is equal to Tn by 8 plus 1. So if you just put this value of Tn by 4, that is Tn by 8 plus 1, in equation 2 at the place of Tn by 4, then this entire equation will become Tn is equal to Tn by 8 plus 1. Just check this all thing which I am marking here. This thing is Tn by 4 plus 1 plus 1. I hope you are understanding. This is equation 3. So are you getting some pattern here? Yes, definitely we are getting a pattern. You just see when we have Tn by 8, isn't it? In the latest third equation, we have Tn by 8. We are having 3 ones. So if you continue, in the next equation, we are going to have Tn by 16. And we will be having 4 ones. Isn't it so? So basically, we are getting a pattern here. Just try to understand. It is Tn is equal to Tn by 2 raised to k plus k. Just imagine this k is 3. K is 3. Then this form, the left of the plus here will be Tn by 2 raised to 3 because it is 2 raised to k. So Tn by 2 raised to 3 is Tn by 8. That's what we exactly had in equation 3, isn't it? So whatever is k, like k is 3, then we are exactly getting n by 8 here, Tn by 8. So this is the general form that we have got. Let's name this equation as k. Now starts the fun part. Now starts the interesting part of substitution. Now you know that this will continue Tn by 16, Tn by 32, Tn by 64. But when is this going to stop? We know that T1, given the data, given the base case, T1 is exactly 1, isn't it? So we know the value of T1. This is the base case. And somehow, we want that on the right hand side of Tn, on the right hand side, we should get T1. Are you understanding? That means we want this right hand side. Here I am marking this Tn upon 2 raised to k to become T1. When this right hand side will become T1, the recursion will stop because T1 is 1. So that means whatever I have written in the bracket here, check these brackets, whatever I have written in the bracket here, n upon 2 raised to k should become 1. Isn't it so? Should become 1. So n upon 2 raised to k should become 1 to stop this recurrence. That means n should become 2 raised to k, isn't it? Now, if n is equal to 2 raised to k, we are saying, then k is equal to log n. Of course, log n to the base 2, isn't it so? For example, if 8, no need to explain this, I am sure. If 8 is 2 raised to 3, notice, yes, 8 is 2 raised to 3. Then this is k, isn't it? We are talking 3, value of k. Then k is nothing but k is log of, it is log of log of 8 to the base 2. Yes, that's k. K is 3. So hence we got the value of k as log of n, of course, to the base 2. Now the last thing is that just substitute this value of k in the equation k. This value of k that we have got, k is equal to log n, you can just put it here in the equation k. Wherever k is found in this equation, just put log n. So this equation will become Tn is equal to Tn by 2 raised to log n, isn't it? But Tn by 2 raised to log n plus log n, isn't it? You just check on the right hand side, we are getting Tn divided by 2 to raised to log n, because it was 2 raised to k, isn't it? And k is nothing but log n. Now don't get afraid on seeing this equation, because everybody knows 2 raised to log n is nothing but n. Yes, this is n, come on. Just find out, very silly, childish explanation I am doing. You see this, that suppose n is 8, imagine n is 8. I am not proving this, there's nothing to prove in this. But if n is 8 and we say what is 2 raised to log 8, because n is 8, isn't it? 2 raised to log n, I'm questioning. What is 2 raised to log of 8? Of course, to the base 2. To the base 2. Now everybody knows log of 8 to the base 2 is 3. So this is going to turn out to be 2 raised to 3. Oh, which is n, which is nothing but 8. So 2 raised to log n is nothing but n. So what will this term become in the bracket here? N upon 2 raised to log n is nothing but n upon n. N upon n is 1. That's the way how I have written here. Just observe this. Just observe this equation. After substituting the value of k, I got Tn is equal to T1. I hope you are understanding. And then plus k here of this equation k, this k is nothing but log n, isn't it? So I got Tn is equal to T1 plus log n. And what's given in the data? Given that T1 is 1, we get finally T1 is 1 plus log n. But you notice this is a polynomial of degree log n. So we are going to write Tn is equal to O log n. So the complexity of this particular recurrence relation is O log n. Now, trust me, actually, you might find this to be quite cumbersome, the dividing functions, and more examples will be more difficult, because we are going to get some remarkable series, mathematical series, summations and all that. And many times we'll get geometric progressions. So one might wonder that how are we going to solve this in the gate exam? But trust me, there is something called Master's theorem, and Master's theorem is such a good theorem that it can solve these recurrence relation within seconds. The dividing functions, I am talking about dividing functions. And but I have not directly taught master's theorem. I just want to give you an in-depth idea about the dividing functions. In the next coming videos also, we will be solving substitution. We'll be doing this by substitution method, and only after we have seen the difficulties of solving these recurrence relations using substitution, we will then trust master's theorem. Thank you very much.